All right, everybody, welcome to Earth Science. So we'll start with a warning that every day, Alaska is under attack. And if you were to go down here towards the lighthouse at Selkirk, you'd see the results of that because day by day by day by day, bit by bit by bit by bit, tiny little particle by tiny little particle, Alaska is washing away out into Lake Ontario, gone forever. We're slowly getting smaller. We're slowly getting beat up by the atmosphere. Now, is there places where there's accumulation or deposition? One of the things we got to do in this unit, yeah, like all this beach sand and all of the dunes that are up towards the state park up here, all these nice big dunes. That sand was brought in somewhere and dropped off. But the nets, the overall, if you look up towards town, is that with all of the weathering that's happening, breaking down the bedrock, all of the erosion that's happening as the streams wash away that sediment, we're losing Pulaski little tiny bit by little tiny bit by little tiny bit. All right. So, given that warning, that's the big theme of this chunk of class that we're doing. We're going to do this marking period, basically a little bit with groundwater, and then get into the rocks and minerals themselves before we get to report card time. It's really a continuation of the last unit. The last unit was weather, which the water cycle is really locked up tightly with. I mean, I don't think I specifically talked about the water cycle when we did weather, but I guess it's implied. I mean, you're talking about water evaporating into the air, rising, expanding, and cooling, and going through condensation and forming clouds. We talked about precipitation. We didn't really talk about this last part, though. What happens once that precipitation hits the ground and runs back? It's always beating up on Earth's surface. So all exposed bits are being beat up by the atmosphere. And then let's remember this whole idea that, in fact, I wouldn't mind if we wrote this. And if you were focused in last week, you know this. Landscapes are a result of two things. Stop talking for a second. Can you come up with those two things? What would determine what an area looks like in terms of like Pulaski looking the way it does? It is the bedrock that makes up Pulaski. That's sedimentary bedrock. Those layers you can see exposed down by the Salmon River, and climates. For the long-term weather patterns that interact with that bedrock and beat it up year after year after year after year. And those give us that, like, the balance of those two is why Pulaski looks the way it does. Okay. So the process that we have to understand to go through this bottom part of the water cycle and, in fact, eventually lead to sedimentary rocks is weathering. That's going to be your first chunk of labs. Erosion. I'm not sure I'm going to have a lab for that I can do through YouTube, but I'm going to work on it. And deposition. And those three are really going to carry us for a while. We got to untangle all three of these. So what is it? What are the three? How can we define these in really simple terms? I don't want to do fancy dictionary definitions. Weathering, the breakdown of rock. Go to the Salmon River, look for a place where a rock fell out of that cliff onto the ground. That's weathering. It's physically breaking off of the preformed bedrock, which maybe we should note. I'll do it in a different color. Creates sediment. Sediment is going to be our catch-all term for little bits of rock. It could be anywhere from a giant boulder down to, well, we have official sizes: boulder, cobble, pebble, sand, silt, and clay. Should you ever need them, here's a reference table that has them all. This reference table is like, how fast does water have to be going to move those different particles? We'll do it eventually, but for today, these are like officially the sizes of particles, the sizes of sediments. So if you sit down there at the end of the Salmon River, you're not going to watch boulders rolling down the river. That river doesn't go fast enough. But can you see sand, silt, and clay suspended in the currents or bouncing along the bottom and being dragged out to Lake Ontario? Absolutely. Those are smaller bits of rock that were created by weathering. Weathering broke down larger bits of rock into smaller bits we call sediments. Erosion, I'll go back to black if it matters, is the movement of sediments if you've ever heard somebody say, "Oh, my land is eroding," if like a river's going by, or you got a ditch at the end where meltwater runs down and you see it getting brown and muddy, that's eroding particles. You're losing your land. It's being moved by natural forces, wind, water, waves, things like that. And then eventually, as that stuff all moves down stream, it'll eventually get dropped off, land somewhere. All right, so the whole unit, like in a sentence, is that all this weather stuff we studied in the last unit beats up the rock and breaks it down, takes that stuff, that sediment, and moves it in streams and rivers and in wind, and then drops it off somewhere, generally in bodies of water. And again, you can see both in shoreline environments because all of the sand got there by deposition. In fact, if you go down to where I live, let's take a field trip. Yes, I drive too far. So the beach is over in my neck of the woods. Like we like to go to this one out here. We'll see if we can tell if it's cobbles. Or you can do this right by campus too. If you've ever been to Rudy's, right by campus. Can't really tell. Those are all like cobblestones, round hunks of rock about yay big. And they vary in size maybe a bit. And they come from some of these, we got big bluffs out here. So these big bluffs have worn down, dropped off sand and rocks. The rocks are heavy enough that they pretty much stick around. They move around a little bit with the ice. The sand and silt and clay, though, is light enough that it moves its way up the shoreline and eventually gets dumped. I mean, you can kind of see it in Google Earth here. See how the water looks a little bit turbid? And depending on, I guess depending on what the satellite, what resolution they were using, it's easier to see in some spots than others. But long story short, or short story long, that gives us all the sand that we've accumulated down here in these dunes. All right. So usually I do a couple silly activities, like you've got to make a comic strip that involves something breaking down, that thing moving, and then it getting dropped off, and people come up with all kinds of morbid stuff. But it's an important, it doesn't feel like much right now, right? But it's an important little distinction to make, that these three steps are what are constantly beating up or constantly changing the surface of the earth. And it's hard. The earth is so old. We're all so young, even the older amongst us, that we don't get to observe the large scale changes of the topography of Pulaski. We don't live long enough lives. But you got to see this in a geologist context, that over even 10,000 years, I'll say 10,000 years is still a very short amount of time geologically, but that'd be when the last ice age came through here, about when it receded, and that had a big effect on the landscape. But for those last 10,000 years, it's been just a very slow process of this weathering, this erosion, and this deposition. So we've got to do, if I don't run out of time, we've got to do the two basic types of weathering. If you want to take a pause and a stretch, now would be a good time to do that. We're going to shift gears a little bit and break down our two types of weathering. Okay, so let's do it. First one is going to be called, it's these two terms, we can essentially use them interchangeably: physical or mechanical weathering. And what these mean is that the earth is, and I'll use physical in the definition, I know that's not great, but it's physically being broken into smaller chunks. There's things that naturally happen that physically break down rock. I got a bunch of pictures. We'll shoot through them pretty fast so that we don't make this video too long. Well, it's a weird view, but whatever. So frost wedging, if you've ever accidentally put something into the freezer saying I want to get it cold fast, and then you find out that soda can exploded, you've gotten in trouble and understood the premise that when water freezes, it expands. It occupies more volume as a solid than it does as a liquid. So if you get water seeping into any cracks in rock in any way, shape, or form, when the temperature goes below freezing, it'll expand. It'll open that up a little bit. And then if you get time of year in say fall or spring where that's going back and forth and back and forth and back and forth, you can do this every day. And any place where you get rocks, this is Tinker Falls down by Labrador Ski Mountain, Labrador Hollow Unique Area. This is up towards the top of Cascade Mountain in the Adirondacks. But if you get cracks in rock, I mean, this is old, hard rock, but still there's a crack there. And if it's wet and then it freezes, it's going to expand. These cracks are slowly going to get bigger and bigger. In fact, they're probably microscopically bigger now than when I took this picture, which was probably 15 years ago. So they're probably bigger now. This is an incredibly cool area. If you're ever going to Philly for some reason, plan some extra time. Hickory Run State Park on the Northeast Extension in Pennsylvania. The bedrock here has been completely shattered by freeze thaw. In the Ice Age, the ice didn't make it down this far, but this would have been just past the furthest descent of the glaciers during the Pleistocene, during our most recent Ice Age. So it melted, it froze, it melted, it froze, it melted, it froze. So you end up with like this pile of boulders that's really deep, like 10, 15 feet deep and unbelievably big. There's a couple of them, like multiple football fields, the size of our campus here at Pulaski. Huge. And in one place, there's actually a river like 15 feet below these rocks. You can like walk over the top of it and hear it. It's a really cool spot. There's me as a youngin. But frost wedging, I mean, all the boulders are the same. So these weren't brought in from anywhere else. Like if you go to the Cobble Beaches by Rudy's, all the rocks are different because they were all carried here by glaciers. This is all the bedrock is the bedrock that was in place. It's just been pulverized by frost action, by freeze thaw. I had another one. Oh, there it is. My thing's out of order. This is the top of a mountain in Colorado. Same deal. I don't know. It doesn't want to go. Sorry. Same deal here. This is isn't technology wonderful? This is bedrock that's been pulverized by frost action. Okay. So maybe we'll note that quick here. Frost wedging. Not wetting. Frost wedging. When water freezes, it expands. And that can open up rock. Yeah. Now that can work in tandem with this guy over here that we'll note. So we'll go back to the PowerPoint for root wedging. I'm assuming let's look at this one first. So you can see all the trees in the background. This was in Colorado somewhere. Whatever kind of tree this is, you know, its seeds, its cones, however it works, got dropped in this tiny little crack in the rock and it's growing and growing and growing. And through the years, these roots have an unbelievable amount of strength and ability to break open rock. If you've ever seen dandelions like coming right up through a sidewalk or a driveway, that's it. That tiny little weed is capable of doing that. These forces are really, really strong. This one was in northern Minnesota, and you can see the root like right along the crack of the rock has found its way, and I'm sure it's shooting straight down into the rock as well, breaking it open. This is at the same place as this. This is, I believe it's Fillmore Glen State Park, but I got some plants, and you can see their roots trying to like search, find somewhere, and they find the little crack in rock, get in there, plant gets bigger and bigger and bigger, and it can just break this rock right out. This is relatively weak rock anyway. This is shale, similar to what you see at the Salmon River. Some of those rocks at the Salmon River, you could go and just pull it out. It's not a super strong rock like in the Adirondacks. So plant roots, no problem, busting that all to pieces. And maybe there's a combo like this. We did this in the spring, and you see where it's like stained yellow right there? That's probably where the stack of shale was like right in there. And between frost wedging and root wedging, those two working together, it busted it right out and knocked it out. All right. Earth's surface under attack by these weathering processes. All right. There's the bell. Looks like I'm babbling too much. I'll be back. Okay. I'm back. And my 7th period class is going to be nice and quiet while I record this video. So yeah, that's all root wedging. The only one I didn't do is one of my favorite pictures of it, which is this guy right here, where you can really see that through time, this tree has grown and grown and grown and completely shoved apart those two rocks and built up some soil here as it's grown through the years. This is up in the high peaks as well at the bottom of Lower Wolf Jaw, should you ever climb high peaks. All right, good example of root wedging. So let's chuck that in the notes. Just got to remember where we were. I hope that all of this works. Yeah. So root wedging, roots, break apart rocks. Again, that's going to be like weathering is breakdown, and all of these are different ways to physically, mechanically break down rock. One you don't see very much, but I like it, so I'm going to throw it on there. Yes, is exfoliation. If you know what an exfoliant is, you like rub it on your skin to take off the outer layers of your skin. That's a thing people do, I guess. Um, so this is Rocky Mountain National Park. And what would have gone on here is that this rock would have been deep underneath other rock that through a bunch of geological events, that upper rock that's up here is now gone. It's eroded, it's weathered and eroded away, which means there's a lot less pressure squishing down on that rock. And in the notes, the little diagram attempts to show that. Like back here, there's a dinosaur, so we're in the Mesozoic. There's this much land. 65 million years past, that much land is eroded away. And now, since there's not all that overlying burden on the rock, this unit can like expand. And when it does, it breaks off in these like sheets. It's exfoliating itself. The joints you see in the rock are all kind of rounded off, and these things would slide off in sheets. I think it's a cool one. It's not super easy to spot. This was me. I told my wife to take me a picture, one of those pictures where it looks like I'm pointing at the exfoliation jointing, and she missed significantly. But that's it in the background. This was my wedding weekend. All right, then there's like all of this under here as it's filled in with soil. That would probably be filled with all of the busted off sheets of that big rock body right there. Not a big deal really to like memorize that, but just to stick it in your head as part of the picture of rock physically breaking down. Exfoliation. Cool. And that's more root wedging. This one is like kind of the same. I don't know if I've never been somewhere where this happens, but in deserts where there's huge swings daily from hot to cold, from hot to cold, from hot to cold, the rock expands and shrinks and expands and shrinks and expands and shrinks. And my seventh period class did promise they were going to be a little quiet while I do this, right? Seventh period class, whose name I won't put on YouTube. Yeah. More mechanical weathering. Don't panic about it. All of this physical ways to break down rock. All right. One more thing, then we're done with this long video. Take a break right now if you need to. Last one we'll do is chemical weathering, which everywhere where this one over here is like physically breaking rock into smaller pieces, this one is happening on like a molecular level. This is chemical reactions that go on that break down the rock. If you've ever been to a cave, I know Howe Caverns is a local one people see sometimes. I don't know, it's the only one I can think of close. Those are usually limestone, and what happens is that everything we're looking at here is dissolving. If you have put salt in water or sugar in water, there's a slight difference there chemically that you'll learn in chemistry, but you dissolve it, right? It was a pile of salt, you put it in the water, you stirred it, and now it's salt water. You don't see any solid salt anymore. It's dissolved away. Limestone has this ability. This is going to be a word that I know pops up in one of these labs, so let's check it out now. Soluble. What this means, if I can make my font a little bigger so you guys can see it. Like the ability to dissolve. And again, that's one of my like usual, that's not a very technical definition you're going to see in a dictionary. But limestone is a rock that's soluble, which means it can dissolve, dissolvable, if you will. So when rain hits this, the carbon dioxide in the atmosphere gets into rain and makes a weak acid, carbonic acid. All rain is naturally slightly acidic. Acid rain is a pollution problem, and that is a thing too. But even in the absence of pollution in humans, this happens. And weakly acidic rain will dissolve soluble rock, right? So let's go, where's that PowerPoint? This is Clark's Reservation State Park, which I really recommend you go to. Another great one. Limestone bedrock. And if you can see how it's all kind of like rounded off, like where the cracks are, there's a little bit better angle. Where all the cracks are, these have gotten like really wide. Like you could, if you're not paying attention, you're going to fall right. A leg will fall right in there. You won't get swallowed up in a deep hole. But it's all rounded off because it dissolves in weakly acidic rain. All right. That's it. Now, that could lead to caves. This is exactly how caves form. But we'll worry about the nitty gritty on that another time. Here's some others, and this gets more technical than we need to. You would need to do some chemistry, I think, too. We also haven't talked about what feldspars and these minerals are. But suffice it to say, all of these cover ways in which the rock is chemically attacked. Yes, the roots might get in there and physically crack a rock into two pieces. That's over here. That's mechanical physical weathering. This is turning it into ions. Ions are just, it's a fancy chemically accurate way to talk about dissolving. Create different minerals, break it down on a chemical level. Okay. Yeah, I think that should just about do it. Do we want to say anything else over here? They're all just chemical reactions, really, is the long and the short of it. Okay. That's it for right now. All the rest of the scary stuff, I'm not sure what parts of it we're going to get to or not. I put it all together just in case we have time. We'll do some sections, but not all of it. So don't panic on it, but it'll be there and ready for us. Let's just go back. Big themes. Earth's landscapes are formed because of this balance of the type of bedrock and the climates, and they're constantly being beat up by weathering, the breakdown. Did a lot of that today. Erosion, the movement of that sediment that's coming up, and deposition, or the drop off of the sediments. Thanks for your patience. How long do we go here? The whole 22 minutes. All right. Good luck with the rest. Thanks, seventh period, for being quiet.